Exponential growth describes the growth in a quantity where the growth is multiplicative rather than additive. So an example of additive growth would be, for example, if you deposited $10 in your bank account every week it just grows by $10, and I could say, okay, after 52 weeks or a year, that would be 52 times 10 or $520. Exponential growth describes when there is a percentage increase. So for example, if your account balance increased by 1% every week, that might be $10 in the first week, but it would be more the second week because 1% of your new balance would be a larger number than $10. And that increase in those deposits compounds and accelerates over time, and it can lead to very large increases, which we describe as exponential growth. This is relevant for us because, for example, as people have greater energy demands, as the population grows and as the standard of living rises around the world and people move to a more energy intensive society, our demands for energy are increasing exponentially, but the available energy is not increasing at all. In fact, it's a constant, and the fuels are, of course, being depleted. Not only are they not increasing exponentially, the amount of fixed fuels is set by the history of the planet. So the amount of fossil fuel, the amount of uranium, those aren't going up at all. It's just going down. Whereas flows like solar and wind are constant. Fortunately, we're currently only using a small amount of them. So to understand how much our demands are and how that will evolve over time, and this will also come into play with the climate later, let's take a look at exponential growth. So in the slide here, you see a couple of equations that describe the number of something, which we describe as n, in terms of an initial number, n sub 0 or n naught, and the rate of growth, r, and the time for that growth that growth is happening. Now, we're not going to need to deal with those two equations up there. Fortunately, there's a shortcut that's very easy. It's very handy to have in your back pocket as you go through life if you're looking at mortgages or loans or student loans or savings, that is circled at the bottom of the slide, and that is that the time for something to double in quantity, called the doubling time, is approximately equal to 70 divided by r, where r is the percentage growth rate, and the units of this are the time units associated with r. So for example, if something is growing by 10% per year, then the units for this, and what I'm going to call t double, would be 70 over 10 years. And it's years, not days or months or seconds or something else, because this percent rate is 10% per year. I didn't write it before, so let's make sure we write that now. If it's 10% per day, then the doubling time would be 7 days, not 7 years. So on the previous slide, I gave a question for you about the population increase of tribbles. And tribbles are little furry creatures from Star Trek, and they procreate quite rapidly. And I believe we had a 10% weekly growth. 10% per week is the growth rate of the tribble population. And so the question is, how many tribbles would you have after 1 week, 2 weeks, 3 weeks, 4 weeks, etc.? So let's write the number of tribbles and the time. And let's say, as it says in the slide, that we start with 100 tribbles when we start our clock. After 1 week, 10% of 100 is 10. So we add 10 tribbles. So we would have 110 after 1 week. Now let's say we want to figure out how many tribbles there are after 1 year or 52 weeks. Well, I could go through this and write down 52 elements in my column, but I can use this shortcut that says that the doubling time for tribbles is T double for tribbles is 70 over 10%. That's 7, and it's weeks, not years, because they're growing at 10% per year. So after 7 weeks, how many tribbles would I have? I would have, that's one doubling time. So starting from 100, I double it, I get 200. So then I don't have to go through the 110 plus 10% is 121. What's 10% of 121? 3 weeks, add that all up. I can just jump to the doubling time. Now, if I wanted to know exactly how many there were after 18.3 days or something like that, then I would have to use those equations on the last slide. But we're not going to worry about that level of detail. So how many tribbles would there be after 14 weeks? Well, I'm doubling the number that I started with 7 weeks prior, which was 200. So that leaves me with 400 tribbles after 14 weeks. One more doubling time. Doubling time is 7 weeks, so I don't double the time. I go one doubling time forward, so 7 weeks plus 14 weeks puts me 21 weeks in. I do double the number. I would have 800 tribbles. 7 weeks more is one more doubling. So after 28 weeks, I would have 1,600 tribbles. After 35 weeks, 28 plus 7, one more doubling time, I would have 1,600 times 2, or 3,200 tribbles. And then after one more doubling time of 42 weeks, I would have 6,400, doubling 3,200. And finally, after 49 weeks, which is a little bit less than a year, 6,400 doubled would be 12,800 tribbles. And you can see how that's a really handy shortcut if I'm going to be looking at multiple doubling times rather than just going increment by increment. Week by week, for example, would have taken me a long time to get to this number. And if I wanted to say, okay, what is it in a year exactly? Well, 49 plus 7 is 56 weeks. 12,800 doubled is 25,600. So a year is somewhere in between there. And so the number of tribbles after exactly 1 year is going to be somewhere between 13,000 and 25,000. And that's a big uncertainty, but we can at least get a kind of ballpark picture there. So this is what you need to know about exponential growth. You need to know how to use this doubling time. And you'll be using this also when we talk about nuclear power, nuclear energy, because exponential growth plays a role in um, uh, chain reactions. And then we'll be flipping it around and talking about exponential decay, because as nuclear fuel is burned up in a nuclear reactor, half of that, well, the radioactive fuel decays with a half-life, so that after a certain period of time, half of it is decayed. It's sort of the opposite direction of this exponential growth, but we'll use the same kind of principle that we've used here to describe exponential growth.